Welcome to Mastering Solutions. In this question, we're combining some principles from previous chapters that we've done. And so with this, let's start on part A, and let's figure out how far away we need to place the paper to get a clear image. We've talked about this in a lot of previous questions. I'm going to show you mathematically, and I'm going to show you conceptually. I think it's really helpful to understand both because it rounds out your understanding better. So for part A, we can use the thin lens equation to figure this out. 1 over f is equal to 1 over s plus 1 over s prime. But if you think about this, the object distance, meaning the sun, it's way further away than our focal length, right? Like a lot. So it's way bigger than the focal length. So if the object distance is huge, much bigger than the focal length, we can treat it as if it's at infinity. Now, the term that we use in optics is optical infinity, which doesn't mean a infinity in the way you normally think of it. It just means it's so far away that dioptrically, it doesn't really matter. And so as this approaches infinity, that means because it's in the denominator, this whole value is approaching 0. So if we rewrite that then, assuming that this essentially is non-existent, then that means that 1 over f is going to equal 1 over s prime. And if we take the reciprocal of both sides, the focal length is equal to the image distance. So we just figured out mathematically that the best place to place the paper is going to be at the focal length of the lens. Now, we've talked about this a lot in the questions when we would do ray tracing, because if we have a lens here, and here's the focal length, and this one they say it's what, 10 centimeters? So if we have light rays coming from really far away from the sun, they're for all intents and purposes parallel to each other. Now, it's not really possible to get truly parallel light rays, but the sun is going to be as close as we're going to get. And so as these parallel light rays come in, that is collimated light. Collimated or parallel light rays focus at the focal length, right? So they're going to focus right here. They'll all cross right through that focal point there. So this is the conceptual way to think about that. To get the clearest image with these parallel light rays, put it right at the focal length. So the answer for part A is going to be 10 centimeters or at the focal length. Now, if we go to part B, we need to figure out what's the diameter of that. But if you think about what the diameter is, that's we're dealing with a circle, right? It's the sun. So the top to the bottom of the image is the height, but that's the same thing as the diameter. So we can use the relationship. We've used this in a lot of previous questions. H prime is equal to H times S prime over S. Now, a lot of the questions that we've used, we've had a negative value here. For this case, we don't need to worry about it. You can think of it like we're taking the absolute value of this. And so if we have H prime, or the image height, in this case the diameter, the object height is going to be the diameter of the sun. Well, this is a little tricky thing they're adding in here to try to make your life harder. We have 1.4 million kilometers. So if we have 1, 2, 3, 4, 5, 6, some students would be tempted to put in 1.4 times 10 to the 6 meters, but that's not correct because we also have the kilo, which means 10 to the 3. So really we should add another 3 zeros to put this in meters, right? So it's really going to be 1.4 times 10 to the 9 meters. Same thing with the distance from the sun to the earth. So now we have the image distance, which in this case we said was the 10 centimeters, so 0.1 meters, divided by 1.5 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, plus 3 more is 11. So 10 to the 11 meters. And that's going to give us the diameter. So we have 1.4 times 10 to the 9 multiplied by 0.1 divided by 1.5 times 10 to the positive 11. So that gives us 1, 2, 3, 4. So 9.4. Let's do it in millimeters. So 1, 2, 3. So we have 0.93 millimeters, or 10 to the negative 3. So that is the diameter of our image of the sun, which obviously the diameter is the same as the height of the image in this case. Okay, so moving on to part C, we need to figure out the power of that light, and we're told the intensity. So we need to use the intensity formula. If you remember way back, intensity is equal to the power divided by the area. And so if we arrange this for power, we'll multiply both sides by area. So power is equal to the intensity times the area. And now we're dealing with a circle, and it's not a sphere. There was one question where we were dealing with like a light bulb, and we had to use the area of a globe. But in this case, it is on a paper, so we'll use the area of a circle. So we're going to do power is equal to the intensity times the area of a circle, which is pi r squared. We're told the intensity, which was the 1050 watts per meter squared. So 1050 watts per meter squared. Okay, so now we can multiply this by the area of the circle. But what circle are we talking about? Just a moment ago, I was talking about the paper. That's for part D. For this part, they're talking about what's the power that we're capturing at the lens. And so here we need to use the area of the lens. And so we have pi, and then we had a diameter of the lens of 4 centimeters. And so we're going to divide that by 2. So we have 0.02 meters squared for the radius of the lens here. So that's going to be 1050 times pi times 0.02 squared. There we are. And so we have 1.32 watts. And now I'm going to keep the 1.32 for the next one. You could, for significant figures, put it as 1.3 if we were to round that. But that's the answer for part C. And now last one, let's move on to D. Now we need to figure out what's the intensity of the sunlight that's focused down into the image. So now we're going to use the same equation, but we already have it solved for intensity with the power over the area. So for this one, we're going to use the power that we just solved for. So intensity is equal to the power, so the 1.32 watts, and divided by the area of a circle, in this case now the image on the paper. So we have pi times the radius, and so 0.93 times 10 to the negative 3 meters is the diameter. So if we divide that by 2, that's the radius for our image on the paper, and we square that. So we have 1.32 watts, and then we're dividing that by the area, and we said it was pi times the radius, which we said was 0.93 times 10 to the negative 3, and then that needs to be divided by, and then that is all squared. So that gives us an intensity of 1, 2, 3, 4, 5, 6. So we have the intensity for the light rays getting focused is 1.9 times 10 to the 6 watts per meter squared. So this is the intensity at the paper. The power at the lens is 1.32 watts. And then for part A, this is where you place the paper to get a clear image. And then this is the diameter of the image.